Imagine teaching a robot to draw a perfect cat, but all it has to learn from is a pile of blurry photos and random scribbles. How do you guide it to really understand what a cat looks like? In machine learning, this is known as distribution matching, transforming one data distribution, say, a messy, scattered set of points, into another like the clean, structured shape of a real cat. And one of the most powerful tools for achieving this: optimal transport. Think of it like a city planner trying to move people from their homes to workplaces in the most efficient way possible. Optimal transport finds the least costly way to rearrange one distribution, a crowd, into another, a new layout. But here's the problem. Computing this perfect path in high-dimensional space is computationally infeasible. So researchers turned to a brilliant shortcut: sliced optimal transport. Instead of solving the full high-dimensional problem, we project the data onto random lines, slicing it into one-dimensional problems, and solve the simpler matching task along each slice. It's like asking, on this line, how do I move these dots to match the target? Then we combine all these local solutions into a global transformation. And that's where the slice matching scheme comes in, an iterative algorithm that gradually pushes the source distribution closer and closer to the target. At each step, we pick a random direction, apply a slice matching map, and update our distribution. Over time, it converges, but how fast? And under what conditions? That's exactly what this new research answers: quantitative convergence rates. Not just it works, but how quickly and why. The team proved that when matching Gaussian distributions, the error measured by the sliced-wasserstein distance decays like 1 over k to the power of 2 alpha 1, where alpha controls the step size schedule. So if you pick alpha equals 0.6, the error drops faster than if you pick alpha equals 0.55. And the best part? This rate is non-asymptotic, meaning it applies even for moderate numbers of iterations, not just in the long run. But here's the real breakthrough. Why does this work so well? They uncovered a mathematical condition called a Łojasiewicz inequality, a kind of gradient control that ensures the algorithm never gets stuck in flat regions or oscillates endlessly. In simple terms, the gradient, the direction of steepest improvement, is always strong enough to push the algorithm toward the target, as long as the data stays well-behaved. And in the Gaussian case, they could prove that this gradient stays strong because the eigenvalues of the covariance matrix, which control how stretched or squashed the distribution is, remain bounded. But there's a crucial twist: how you choose your slices matters. If you pick just one random direction at each step, the distribution's shape can jitter wildly, like a drunk person trying to walk in a straight line. The algorithm becomes unstable, and convergence stalls. But if you use a full orthonormal basis, meaning you match all orthogonal directions at once, the algorithm becomes much more stable. The eigenvalues stay bounded, and the convergence is smoother and faster. This isn't just theory. The researchers ran simulations, matching Gaussians in dimensions from 5 to 100, and confirmed, using orthonormal bases leads to faster convergence and less noise. Even more exciting, they tested this on real-world data, discrete samples from Gaussian mixtures, and saw the same pattern. Smaller alpha, slower step decay leads to faster convergence than fixed step sizes. So what's the takeaway? Sliced optimal transport isn't just fast, it's predictable. With the right sampling strategy, orthonormal bases, and the right step size schedule, a decaying learning rate, you get provable, fast convergence to the target distribution. And while the theory currently applies best to Gaussian or elliptical distributions, the results suggest this framework could extend much further, especially with small tweaks like regularization. So next time you see a generative AI creating realistic images, remember, behind the scenes, algorithms like this are quietly, mathematically, slicing through complexity to make it all possible. If you enjoyed this deep dive into the math behind AI's magic, hit like, subscribe, and let me know in the comments, what kind of distribution should we match next? Maybe a cat or a cyberpunk city?